Right. Okay, so far today, we've looked at the Cyrus-Beck algorithm. Okay, so that's a way where you calculate how far away your points are from the edge of the window, and you use that to clip the line, depending on whether the distance is positive or negative. We looked at the rather odd one, well, I think it's odd, that Cohen-Sutherland one, which is all about bit codes. Okay, that doesn't actually calculate the clipped point. What it does is it tells you whether you need to clip it, which saves a lot of work, especially when we're dealing with windowed systems. What I'm going to move on to for the last one is a way of determining whether we need to clip a polygon. Okay, so up until now, we've just been dealing with single lines, and this is a method about how we clip polygons. This will also be your part of your assignment 6 as well. Okay, so this one's called the Sutherland-Hodgman. So you have Cyrus-Beck, you have Cohen-Sutherland, and you have Sutherland-Hodgman. They're all named after whoever invented them. So Sutherland bloke is a couple of times. Okay, so the Sutherland-Hodgman algorithm used to calculate vertices of a polygon that is clipped to a clipped region. Okay, so what you have is each polygon in your virtual world is defined by a set of vertices. Okay, so imagine you've got your faces array. Each row of your faces array determines what vertices form that face. So here I have a list. Now this is for a single polygon, so we're just going to take one polygon at a time. And my polygon is defined by these vertices, V1, V2, etc. And each V is a point in your screen space, X, Y, Z coordinates in the screen space. And what we do is each edge of your clip region, the polygon vertices are checked to see if they are in front or behind the edge. And we do that by calculating the D value. Okay, so whether that is positive or negative depends on whether it's in front or behind. Any polygon edge that crosses an edge of your screen space, that is clipped, and that's clipped using Cyrus-Beck, which we did in the first lecture this morning. Vertices behind the edges are removed, they're ignored, because we never bother with them. They're removed from the list and replaced with the new clipped vertices. So you start off with one list, and you'll end up with, or you could end up with a different list because you've had to clip. It's a lot easier done than said, this one. So I put up an algorithm here. Again, can be quite dry when you read algorithms like this. As soon as I go through a work example, it should become clearer. So what you do is you start with, you take each polygon one at a time. So you start with an n-sided polygon, which is defined as a list of vertices, and you also have an m-sided clip region. Now, if you look at the viewing frustum, after we projected that to the screen space, you have a 3D unit cube. That is your clip region. Okay, so you'll have, for your unit cube, you'll have 6 different sides which you need to clip to. 6 sides of your cube. Okay, so in this case, where I said they're an m-sided clip region, n normally 6 because you've got a cube in 3D space. What you do, you loop through each edge. So you've got 6 edges of your cube. You loop through each vertex in your list. So what you say is, okay, if vertex J, which is your current vertex, and the next one are both in front of whatever edge you're on, because you're taking it edge at a time, you add BJ to the list. Okay. If your current vertex is behind and your next vertex is in front, you clip to an intersection point using Cyrus Beck, you add your clipped point to your new list. If, on the other hand, your current vertex is in front, your next one is behind, you add your current vertex and the clipped one. Okay. Like I said, it's a lot easier done than said, which is why I've got a worked example. Okay, so we've got a couple of loops. We first loop it through the edges of our clip region. Then you loop through your vertices in your list. Okay, so here I've got an example. I've got a star-shaped polygon. Rather unusual polygon when it comes to computer graphics. We tend to prefer simpler polygons, but it'll still work. So we've got this star-shaped polygon, and I've got this rectangular-shaped clipped region. Okay. And I've labelled each edge of my rectangular clip region E1, E2, E3, E4, edge 1, edge 2, etc. Okay. And in my star-shaped polygon, I'm starting off with V1, I'm going around, and it's got 10 vertices. So my initial vertex list are those 10 vertices. Okay, so this list defines this star-shaped polygon. Okay, so first thing we do is I'm going to take the bottom edge, edge 1. And the bottom edge has, we always assume that our normal vectors for our edges are pointing towards the centre. Okay, so we take the bottom edge and we loop through our list. Okay, so we look at V1, the line joining V1 to V2. V1 is behind, V2 is in front. So what we do is we clip V1 to this edge. Okay. And we do that using Cyrus Beck. And I label that new point I1 for intersection. And add that to new list. Okay, so new list starts empty each time, and you add things as you go. V2 all the way around to V7, all the way around here, all in front, so I can just add them to my new list. That's easy. V8 is in front of edge 1, but V9 is behind. Okay, so what I do is I clip V9 to the edge using Cyrus Beck, and that's I call my new point I2. So that's my new intersection point. And I add V8 and I2 to my new list. V9 to V10, well, V9 is behind and V10 is in front. So as well as clipping V9 to I2, I also need to clip V9 to I3. And I add I3 to new list. And finally, V10, this one here, is in front of my edge, and V1 is behind. So I clip V1 again. So I've already clipped V1 to I1. I clip V1 to I4, and I add V10 and I4 to the list. Okay, so my new list, at the end of that first step, has grown a bit. So I no longer have V9 and V1 in this list. I've sort of replaced V1 with I1, replaced V9 with I2 and I3, and right at the end, I've also replaced V1 with I4. So that's just one edge. Okay. Now we go to the next edge. Notice how my polygons changed. Okay, so I started off with the list which I had at the end of the previous edge. Okay, do the same thing again. I1 is in front, so we add to the list. V2 is in front, but V3 is behind, so we clip V3 to I5. and add V2 and I5 to the list. Notice the intersection, sort of the number under the I is increasing each time. V3 is behind, V4 is in front. So we need to click V3 again to I6 and add it to the new list. And V4 going all the way around to I4 are in front. Okay, so that's my list after that step. So we start with, at each edge, we start with the current list. We work through the current list and then replacing any ones, any vertices which are behind with the intersection point. Okay, same, pretty much similar thing again. Don't really have to sort of work through this too hard. Okay, so again, we start with I1 in our list. So we're starting here, add I1, add V2, add I5, add I6. We get to V4 to V5. V5 needs to be clipped to I7. So we add V4 and I7. V5 also needs to be clipped to I8. So we add that. Then V6 all the way around to I4 is in front, so we just add them. Okay, and pretty much the same thing again. So we got those 4 points. Okay, so you work your way through the list, having a look at those each edge in turn. If an edge needs clipping, you clip it using CyrusSpec and replacing. You have some new vertices which replace the ones in the old list. So at the end of it, that's after we've done each of the 4 edges. In reality, you've got to test each of 6 sides of your cube. Okay, so at the end of it, whatever your list is, that then defines your clipped polygon, and you just plot your clipped polygon, and then you see it's being clipped. So not too difficult. I hope you sort of get that. It's just a way of formalizing what you're doing when you're clipping. So, remember, computers are fairly stupid things. You have to tell them what to do, and so this is one way in which we do it. Okay, so that's what you get. Actually, I can show you this a little bit better. Okay, so this is a sort of similar to your assignment 5. So this is the world space. Okay, and what I've got here is the blue dot represents a camera, and the green dot represents the way the camera's looking. So that's your world space. So for your assignment 4 last term, it was all about aligning it to the world space. Okay, so there's the aligned world space. So I've moved the blue dot to the origin. Okay, and everything's rotated around the camera. And what I've also done is I've drawn a viewing frustum. So if I look at it through that way, okay, you can see there's the screen. Well, there's my screen, and there's my back viewing plane. And you can see if I just look from on top, you can see, but there's some bits of these houses which are outside the frustum, and there's that bit of that church, and there's a bit of the back church which it was also outside. So the next step, which is this step, it's applying that projection. So this projection, okay, if I look at it from that angle, okay, that's the perspective view. So if you actually look at it from on top, you can see it's sort of been squished and stretched a little bit. So this house here, it's actually the same size as these two. I haven't changed the size. You can see the same size. But because it's further in the distance, okay, it goes smaller by perspective. And it's also, notice I've got the unit cube, so it goes from -1 up to 1 in all directions. So if I did look at it that way, again, -1 to 1. Okay, so you can see, again, that side of that house the side of the church and the back of the church needs to be clipped. Okay, so finally, well, actually not finally, but this is a clipped screen space. So what you can see here is, if I look at it from on top, I've applied Sutherland Hodgman to this. So you can see the sides of those houses have been cut. It looks like sort of I've just taken a big guillotine and cut it down that side. The back of the church, again, has been cut, and so is the side. So if I actually turn that around, you can see it's sort of cut off there. And the back of the church has also been cut off. So therefore, at this stage, everything in my screen space exists, or it exists in my visible sort of area. Still doesn't look very good. Doesn't look like a proper physical world or a virtual world. So I'm just going to run all through that again. This does it all. The next step, which we'll be doing next week, is that. Okay, so this goes from where are we? That's a stage. That's after clipping. Is that one? And what I've done here is done something called hidden surface removal. And so you can see we've got a bit of a more realistic, solid. So this house looks solid. So at this stage, it's kind of like you can see through everything. Doesn't look very realistic. And the next stage is to remove the hidden surfaces. Right, I'm just going to stop the